Now, what is equipotential surface? Equipotential surface suggests that the potential of a surface must be same. That's why its names it equipotential surface. And there is nothing much to read here, but we must know the basic. The basic is, if there is a surface like this, and in this surface every point has the same potential, this surface is called equipotential surface. But there are some properties of this equipotential surface. First of all, we must know that a charge, if we want to place a charge from a point to another point in any equipotential surface, the work done will be zero, because I'm writing this, I'm proving this actually. Say the work done, what is the work done? Work done is dV into Q. What is dV? dV is basically the change of potential. So potential from one point to another point, the difference between these two is dV. As the equipotential surface has the same potential in every point, that's why dV is equal to 0. That is why dW equal to 0, or the work done is 0. So this is the first property. And the second property is the equipotential surface. If we want to draw a tangent in any point equipotential surface, it invariably gives the electric field. Why? Because when we read the lines of force is, what is the lines of force? Lines of force, as we read in the electric field chapter, lines of force is basically when there is an electric field existing anywhere, some imaginary lines or tracks coming from unit positive charge towards unit negative charge, and it is the lines of forces. And in any point of the lines of force, if we want to draw a tangent, that tangent suggests the electric field of that particular point. So electric field, if the tangent of any lines of force is the electric field of that particular point, then equipotential surface has almost parallel lines of forces. So parallel tangents, and the line, the tangents are the electric field here. So this is equipotential surface. Now dipole. Okay. Before we go to the dipole section, we must put here this sphere. What is the potential of a sphere or hollow sphere inside, outside, and on this sphere? It is pretty much easy. So this is a sphere of radius r. And if we want to calculate the electric field, so there is a point which has the distance a from the center of the sphere, and we want to calculate the potential at that particular point. It is pretty much easier, because unlike the electric field, potential is a scalar quantity. Potential is a scalar quantity, not a vector quantity. As the potential is a scalar quantity, so we need not to worry about the direction to calculate for that, and we just need to calculate the value. So what is the value here? Pretty simple. Potential is written as Q by 4 pi epsilon r, and if the medium is free space or the air medium, it is epsilon 0, as we know. So here, what is the potential? Potential is Q by 4 pi epsilon r. R is the distance between the center and that particular point. Now what is the potential on the sphere? Just put R is equal to A, this is 1, and B is equal to Q by 4 pi epsilon A, this is 2, And inside this sphere, when we calculated the electric field inside a hollow sphere, it was 0. Now, as the electric field is 0, E is equal to 0, and as we saw in this part, that electric field is basically the spatial derivative of potential. So if some quantity which is 0 and it is also the derivative of another quantity, that means that particular quantity is a constant. So we can write V is equal to constant. If that is so, then dV dr must be 0. So the potential inside a sphere is a constant. And just I want to draw a graph of this part for a sphere. And if we draw the curve, this is say R and this is potential. So up to, so this is A actually, and this is the radius R. Up to radius R, the potential is constant. So this is the potential, say, if this is on the sphere, and then it is decreasing. I am writing the relation like here V is equal to Q by 4 pi epsilon E. Here V is equal to Q by 4 pi epsilon R. R is the radius. And here also same, V is equal to Q by 4 pi epsilon R.